In this video, I want to do a few more examples of working with the order of group elements. Let's consider the group Z12. I want to find the order of a few different things. The first one I'm going to do is 6, 2, and 6 plus 2. Well, for 6, we would have 6 plus 6, since this is an additive group, is equal to 12, which is the same thing as 0. So the order of 6 is 2. For 2, 2 plus 2 is 4. 4 plus 2 is 6. 6 plus 2 is 8. 8 plus 2 is 10. And 10 plus 2 is 12, which is the same thing as 0. So we have 1, 2, 3, 4, 5, 6. So the order of 2 is 6. Finally, I want to look at 6 plus 2, which is 8. 8 plus 8 is 16. Mod 12 is 4. And then 4 plus 8 is 12. Mod 12 would give me 0. So this time my order is 3. Let's do another one. This time I'm going to do 3, 8, and 3 plus 8. We just found that the order of 8 was 3. 3 plus 3 is 6. 6 plus 3 is 9. And 9 plus 3 is 12. Mod 12 would be 0. So here we have 4. So the order of 3 is 4. Like I said, we just found the order of 8. Now let's do 3 plus 8, which is 11. 11 plus 11 is 22. Mod 12 is 10. 10 plus 11 is 21. Mod 12 is 9. 9 plus 11 is 20. Mod 12 is 8. 8 plus 11 is 19. Mod 12 is 7. 7 plus 11 is 18. Mod 12 is 6. 6 plus 11 is 17. Mod 12 is 5. 5 plus 11 is 16. Mod 12 is 4. 4 plus 11 is 15. Mod 12 is 3. 3 plus 11 is 14. Mod 12 is 2. 2 plus 11 is 13. Mod 12 is 1. And finally, 1 plus 11 is 12. Mod 12 is 0. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the order of 3 plus 8 is 12. The next thing, I want to show that the order of A inverse is the same as the order of A. Let's suppose that the order of A is equal to n. Well, A inverse to the n power. This is the same thing as A to the n power raised to the negative 1. We know A to the n is the identity. And the inverse of the identity is the identity. However, we need to prove that n is the smallest possible integer that works here. Let's suppose A inverse to the m power is equal to the identity, where m is less than n. Well, this is the same thing as A to the m inverse is equal to the identity. I can then take the inverse of both sides. The inverse of the inverse gets me back to A to the m is equal to E inverse. E inverse is just E, so now I have A to the m is equal to E, where m is smaller than n. So I get a contradiction here. So the order of A inverse must be the same as the order of A. Can an element of an infinite group have finite order? In a previous video, I looked at the integers under addition and showed that every non-zero number had to have infinite order. So is it possible I can have a different infinite group with finite order? And the answer is yes. Particularly if we consider the group R star under multiplication. -1 squared is equal to 1. So the order of -1 is 2, even though this R star is an infinite group. So the size of the group does not determine the order. For my last one, I want to show that if the order of A is km, then the order of a to the k is m. Well, first, a to the k to the m power. Properties of exponents say that's a to the km. And since a is of the order km, we know that's equal to the identity. So now we need to show that this is the smallest number. Let's suppose that a to the k raised to the n power is the identity, where n is between 0 and m. So I have a smaller positive integer that gets me the identity. Well, properties of exponents then tell us that we would have a to the kn is equal to e. And we then know that kn is going to be smaller than km, since n is smaller than m. Well, that gives me a contradiction. Since km is the order of a, km is the smallest positive integer that gives me the property that a to the km is equal to e. So this would be impossible. It must be the case that n is equal to 0.